Hello everyone, welcome back. This is Calculus 2. In this video, we're going to talk about 6.2, properties of power series and Tayor and Maclaurin series in 6.3. So this video will be very short because when you're taking any other advanced course, this concept is actually going to be overlapped. But I want to briefly talk about very unique type of series in this video, so you can finalize chapter 6. So let's take a look at 6.2 concept here. So I want to talk about power series. This is a very special type of infinite series, and then there are a couple of characteristic of power series. So I'm going to write down power series. What that means is this is a special type of infinite series, and then that either converges or diverges. So we've been learning many different type of series in chapter 5, harmonic series, geometric series. There are so many different type of series. So power series is very similar to them, but it's a special type of infinite series. So there's no ending. So when you look at this two, series, you will keep adding infinitely. And then there are two cases at the end, whether it is going to be convergence series or divergence series, right? So this is very unique because there's no ending. It is going to be infinitely adding forever. So that's the power series we're going to talk about. So this power series is going to be converges, right, in the following two cases. So if the f and g function is already converges, the addition is also going to be the converges. If you are subtracting, let's say f and g is already converges, okay? If you're adding, if you're subtracting, doesn't matter, the outcome is going to be always converges. So that's the first characteristic of the power series, which is very obvious, right? And second case is a little bit complicated. Let's say you're multiplying two series, and then it's going to be converges based on the the number that you're going to multiply. So this is actually a little bit special. So I will show you the example right there. And then you're not going to see the last case, not a lot, but we're going to focus on the first and second characteristic in terms of the power series. So just remember, when you talk about other type of series, you actually had an ending number. But power series is different from them because there is an infinite ending. There's no ending. So keep adding. And we are checking whether it is a convergence or divergence. And then if those two power series already convergence, addition, subtraction is going to be also convergence, okay? So let me show you that example, okay? Based on those characteristics. So here we go. Let's say I'm going to give you guys, two function, two actually series, power series. So that means you're keep adding A0. So if I'm writing A0 and 0, A1 and 1, A2 and 2, you're keep adding infinitely. And then in this question, they told you this power series is going to be convergence whenever the interval of x is between -1 and 1. So if the x, so actually I have a little bit of typo, that should be x, okay? So there's x1, x2. So if x is between -1 and +1, this power series is always going to be the convergence, correct? Same thing, if you keep adding b0, x0, b1, x1, you keep adding this power series, it is going to be convergence when x equal to -2 and 2. So the x can be, for the first series, could be -1, 0, 0.999999. As long as the x is between -1 and 1, it is a convergence. And then B and series, as long as x is between negative and 2, they're convergent. So I want to find out the following question. Find the interval of convergence. What if you're adding them? Okay, so this is not the calculation question. This is a little bit of a logical question. So what do you guys think? Since the interval -1, is the common interval of convergence of two power series, right? The interval of convergence of summation of the power series is still the common interval, which is -1 and 1. So what I'm saying is, we know that the AN with the AN power series is going to be convergence between -1 and 1. Actually, we do not include them. So there's no equal. And then the next power series is going to be convergence between -2 and +2. We are going to adding them, right? So if you look at this 2 interval, the negative between -1 and 1, this is the overlap. So overlap between two power series, that is going to be the interval of convergence of the summation of two power series as well. So that's your answer, which is not that complicated. Does it make sense to you? So you're gonna find out the overlap if you're adding or subtracting. So you will naturally feel, how to find out the interval of convergence of the multiple power series. Okay. So likewise, take a look at one more example. So I have very unique function. So look at that. We do have, we want to find out the interval of convergence of the following power series, right? And then we know that the AN times x to the n power series, we already know that the interval of convergence is between -1 and 1. So let me modify this power series a little bit. So AN, 3n, xn, and then I can actually combine this 3 times x because they have the same exponent n. So n equal to 0, AN, 3x combined to the n, correct? And then what happened? We already know that infinity power series from AN xn, it is a convergence, right? This is convergence between -1 and 1, correct? So here you multiply 3 in front of the x. So I'm going to write down, we are looking for the interval of the convergence of the possible x. So what we are going to do, think about it. I'm going to write something here. This one also has the same convergence. So since infinite AN, this power series has the interval of convergence between or at -1 and 1, thus, or I'm going to say, the convergence of the interval of, interval of convergence, the interval of convergence of, we are looking for is going to be -1 at -1/3 and 1/3. Why? Because we know that this entire, right, power series, interval of convergence is going to be -1 and +1, because according to the characteristic, they're going to be equal convergence. But we are looking for only the interval of x, right? So therefore, the x interval is going to be between -1 and 1/3, right? So mathematically, you can think about it. I'm gonna make it a little bit smaller. Can I? Yes, can I smaller? So think about it here. We already have a 3. 3 times something something should be -1. So these two numbers should be -1/3 and +1/3. So this is the interval of x's that we are looking for of this particular power series convergence. So therefore, the answer is going to be -1 and 3 and +1/3. Okay, so think about it. This is the how to find out the interval of convergence of a particular power series. Okay, I'm going to talk about the next concept in terms of the power series. So it's going to be more and more and more understandable. So let's take a look at it. So another concept in terms of power series, we're going to think about the geometric series. There are a lot of commonality between geometric series and power series. So for example, if you remember, okay, the geometric series, 1/1 minus x, and then let's say I want to find out the the convergence interval of this particular function. So if you remember, if the x is between -1, because we consider x as a common ratio, then whatever the series is going to be convergence. Do you remember about the geometric series? About the geometric series, if the common ratio r is between -1 and 1, then the geometric series is going to be convergence. If the r is greater than 1 or less than -1, it was a divergence. So we're going to utilize this characteristic of geometric series in terms of the power series, because power series is a very unique special type of series where the ending is infinite. So if your power series is getting involved with the kind of like geometric series type. So for example, I have this function. And then I'm going to find out whether this series is a convergence or divergence. So let me modify this. So as a series form, we're going to write it 1 positive infinity 3x over 1 plus x to the second. So this is a series now. This is just function. And then when I'm looking at the function, right, this is a little bit similar to the geometric series if I modify one more time. So this is the same as 3x over, I can rewrite it 1 minus x to the second. So same thing, this is going to be 3x over 1 minus negative x to the second power. So what do you guys think? This information, negative x to the second power, this is the common ratio. So I can say, right, if this common ratio is between -1 and 1, this entire series is going to be convergence. I want to find out that interval of those x's. What other possible x's that makes this series is going to be a convergence series, right? So let's solve for x here. I'm gonna multiply negative, negative, negative everywhere, so that you are going to be switch over the inequality. 1 positive and -1. And then I'm going to put the radical on everywhere. So it is going to be 1, x, and -1. Okay. So that what happened? If x is between 1 and -1, this series is always going to be, so specifically, I forgot the negative. So radical 1 is the same as a 1. Radical -1 is a radical -1. So whatever the x is between 1 and radical -1, this series is a convergence series. So you can find out the interval of convergence of this particular power series by using the characteristic of geometric series, because we know that as long as the ratio is between -1 and 1. So I modified this function like 1 minus r form so that you can find out. Okay, so we are getting better and better. So let's take a look at one more example. I'm going to give you so many, different type of functions. So let's say I have this function. I want to know, right, where is the interval of convergence? So 1 to infinity, 1 over. I want to find out the interval of x's that makes this power series become a convergence series. So this fraction is not really, relevant to the geometric series, but if you remember, this is more relevant to partial fraction. So what I'm thinking is you can do the decomposing, so you can find out the partial fraction, and then we're gonna take the, we're gonna, find out the commonality of the geometry of each fraction. So maybe we can find out the interval of convergence. So let's do the decomposing work to find out the partial fractions of that fraction. So let's do the work. First, we have, I'm gonna actually get rid of, let's get rid of this because I need a space. So we have a 1 over x minus 3, x minus 1, x minus 3. Let's find out the partial fraction. So this is going to be, this is already factored form, if you remember. So it is a over x minus 1 plus b over x minus 3. So these are partial fraction. We are working in a decomposition process. So we're gonna do what? You're gonna multiply x minus 3 here. You're gonna multiply x minus 1 here. So it's going to be a x minus 3 plus b x minus 1 over x minus 3, x minus 3. So we have common denominator. Now I'm going to do all the distributive property. So ax minus 3a, bx minus b, x minus 1, x minus 3. I'm going to combine like terms. So ax, bx combining like term. So a plus b, that's the x family. -3 plus, minus b, that's the number family. So it is going to be corresponding to this one, correct? So they're going to be corresponding. So a plus b, I don't see any x family in the numerator. So what happened? That means a plus b should be 0. -3a minus b should be 1. So that you have 1 from the same numerator, each other. So this is a numerator, right? We have only 1. So this is going to be corresponding this. And then there's no x, a plus b should be 0. So we're going to find out a and b. So it's addition. So minus 2a equal to 1. A is going to be -1 over 2. And then if you're plugging in, b should be +1 over 2. Excuse me. So we found out a and b. So let me complete the partial fraction. So we got 1 over x minus 1, x minus 3. It is the same as what? It is a over x minus 1 plus b over x minus 3. So we found out what the a and b. So it is 1 over 2 x minus 1 positive 1 over 2 x minus 3, correct? Okay, so now I'm going to rewrite this information. I'm going to bring negative 1 over 2 to the front times 1 over x minus 1. They are same meaning, plus, right? And then what happened? This is b. b is 1 over 2, and I'm going to rewrite it 1 over x minus 3. Okay, so I can modify this ugly fraction into the simplify. And then now here, we are going to use the geometric series characteristic. What was it? This one. As long as 1 over 1 minus x, you can find out the common ratio, and that is between negative 1 and 1. It's going to be convergence, right? So let's modify this a little bit. So let me minimize it. So I'm going to change that order. So I have a negative 1 over 2. I'm going to change this order x minus 1 in terms of 1 minus x. So it is going to be, you're going to factor 1, and 1 minus x is the same as x minus 1. So this is I modify by multiplying negative 1 into, or you can factor out negative 1. Same thing we're going to do. 1 over 2. Here, I'm going to factor negative 3 so that 1 minus 1 over 3x is going to be same. So this entire, if you do the distributive property, it's the same as x minus 3. So that's what I modify, because we're going to use a geometric series characteristic. 1 over 1 minus x, and x is between. We can find out this series is going to be convergence. Okay, so I'm going to keep working on it. So now this is double negative change to positive. So if I write better, this is what it is. And then negative, I'm going to have 2 times 3, that is a 1 over 6. And we have a 1 over 1 minus 1 over 3x. So now this is good. We are going to take the series. So we are looking for n equal to 1. Now I want to do here. We are taking the series 1 over 2 and infinity. So we want to know the interval of x where each series is going to be convergence. So what is the method you're going to use? We're going to use a geometric series characteristic. So that would be, what happened? We're going to look at the x. This is the r, 1 minus r. So therefore here, I'm going to bring 1 over 2 to the front. 1 over 6 to the front. Again, we're going to look at the r, right? This one should be between negative 1. This power series will be convergence where that x is between negative 1 and 1. This power series will be convergence where that negative 1 over 3x, or actually not negative, just 1 over 3x, that's the r. R itself, x, is between negative 1 and 1. So let's find out the x. So this is already solved. I'm going to multiply 3, 3, 3. So negative 3, x, positive 3. So what happened? This entire power series will be convergence, right? 1 over 2, negative 1, x and 1. minus 1 over 6, negative 3, x and 3. So again, we are looking for this part, right? And then what is the overlap? So negative 1 and 1, negative 3 and 3. This is the overlap. So the answer is this power series. I'm going to make it a little bit larger. I'm going to write this power series, which is 1 over x minus 1, x minus 3, converges at negative 1 and 1. We just prove it. Okay, so that's something you're going to find out the interval of convergence when you have the complicated function. Usually power series, you can find out the commonality from the geometric series, and then the question can be solved like that. That's it, 6.2. I'm not going to emphasize on too much. 6.2, you can understand what the power series means and how to find out the interval of convergence. Use the concept of the geometric series. Okay, so that's pretty much a 6.2. I'm going to briefly talk about 6.3, Tayor and Maclaurin series. Okay, so Tayor series, it's a very similar. So this is also type of power series, which means they keep going forever. And then whatever the given function. So one of the definition, one of the example of a power series is this. So Tayor series means you have infinite, right? And then they are getting involved with the factorial. N factorial, f, n, x to the n factorial, x minus a to the n. So this is the definition of the Tayor series. So Tayor series is a type of the power series where the series is getting involved with the infinity, especially when you are dealing with this power factorial in terms of your function. So this is actually the Tayor series definition. So if I'm writing, what does it mean? When n is a 0, or you can begin n equal to 1. So actually this one should be 1. So let's begin from 1. Oopsie. So here, so when n is a 1, so f prime 1, right? Or never mind, we can, I don't want to make you guys too confused. So we can begin, let's say just a 0. So I'm going to redo it. So let's do from 0. Okay. So the first term, what do you guys think? If everything is a 0, right? N is a 0, n is a 0. So we have only f of a. Okay, we're going to start from here. And the next one, f prime, n is a 1, a over 1 factorial, x minus a to the 1. The next one, f second prime. So this n prime means you are going to take second time, third time, fourth time, derivation. So then the second time derivated over 2 factorial, x minus a to the second power. And then you're going to keep writing. I'm just looking at the terms, each partial terms of the Tayor series. And then third differentiation over 3 factorial, x minus a to the third, and you keep going forever and forever. So that's the Tayor's power series format. Okay, this is the form of Tayor series. Okay, nothing is special, it's a given. But especially when a equal to 0, I'm gonna write actually more space. Okay, let me change the color. So when a equal to 0 from Taylor series, we call it as Maclaurin series. So that's just different name. So let's take a look at it. Now A is a 0. F is 0. F prime 0 over 1 factorial. X minus 0 is X factorial. F double prime 0 to factorial. X to the second, third, 3 factorial, X to 3, and you're going to keep going. So therefore, the form of Maclaurin series is infinite F and differentiation n factorial X to the n. So this is the Maclaurin series when X equal to 0. So you can see the type of Taylor series and Maclaurin series format exactly in this slide. So if you go to 6.3, they're showing you actually the same, form of Taylor and Maclaurin. But here, I'm going to show you more information. So this is a definition of Taylor and Maclaurin. I'm not going to talk too much in this video. If you're planning to take linear algebra or other, advanced math, this is coming up again. So I'm just introducing what the power series and what the Taylor series and what the Maclaurin series look like. So this is the, kind of like a form of the Taylor and Maclaurin. So now, let's think about it. So in the next slide, I'm going to give you a specific function. So here, let the function is e to the x, okay? And write the Maclaurin series. So this is the question I want to give you. So in this time, we already know what the Maclaurin and Taylor, but I'm going to give you specific function of f of x, which is e to the x, and write down the Maclaurin series, okay? So here, f of x is given e to the x. We already know the characteristic of the e to the x, right? So actually, I forgot in the formula, there's x here, there is x here. So you can see what we are doing. So let's take a look at it. Because to write down a partial, terms of Maclaurin series, we need to see what is the first differentiation, second derivation, third differentiation, things like that. So f of x, I'm going to use the same color. F of x is e to the x. What is the differentiation of the e to the x? Same thing, e to the x. If you do, again, same. If you do more, wow, it's the same. They're going to be same. If you're taking n times the differentiation, it's going to be e to the x, correct? Now, Maclaurin series is especially when a equal to 0, right? So what I'm going to do, I'm going to plugging in 0 into the a. So actually, let me change this x, a. So it's the same meaning, because let's say a. Doesn't matter, it's a same. So according to the definition of the Maclaurin, what is that? We know that infinite n equal to 0, fn times differentiation a over n factorial x to the n, correct? So this is the definition. So especially when a equal to 0. So actually, if I write the definition a little bit better, so let me write it for you. Fn differentiation a right there. So same thing here. So let me write down. So especially when a equal to 0. So n a, that's a clear, right? So we have this, we have this. So this is the Maclaurin series, right? So we know the function is e to the x. So same thing, everything whenever you take the double, triple. So therefore, I'm going to write couple. When a is a 0, so we're going to write it with the e to the x. What do you guys think? 1 plus, right? Because e to the 0, if it is a 0, e to the 0 is 1, right? E to the 0 is 1. Even second prime, same thing. So everything is 1. So therefore 1 plus, the numerator is always 1. So 1 over 1 factorial, what happened? X to the 1. The next one, 1 over 2 factorial x to the second. 1 over 3 factorial x to the third. Keep going forever and forever and forever. And then if I rewrite it, this is going to be infinity x to the n over n factorial. So this is another form of the Maclaurin series. So you can find out a couple more. Okay, so I just briefly explained what the Taylor's series and the Maclaurin series is a very similar Taylor, especially when a equal to 0. So you're going to plug in 0, and then you can keep taking the differentiation. You can find out the same numerator, especially with the e to the x function. Okay, so there are so many, Maclaurin series and Taylor series. So that's pretty much a 6.3. I'm briefly, explaining what it looked like. And then I think if you need more information, take a look at 6.3 so that you can finish entire chapter 6. So we are actually stop here 6.3. And then you can finish all the quizzes, 6.2 up to 6.2. There's no quiz for 6.3, so I'm just introducing what the Taylor and Maclaurin series in this topic briefly, okay? So thank you so much for everyone. So you can finish the 6.1 and 6.2 quizzes. And if you have any question, engage with the other students through the discussion board and always email me. Okay, so I will stop here, and then definitely we finish 6.0 and 6.2 fully, and 6.3 I just introduced so you can expand your knowledge in another math courses in the future. Okay, so I will stop here, and I will see you in the final. And if you have any question, email me. Thank you, everyone. Bye bye.